Alright, silly people, here's the situation. We're back at it again with another matrix-related proof. Uh, this time we're going to be using the common thread fact that the determinant of a transpose of a matrix is equivalent to the determinant of said matrix. I'm going to use that fact, first of all, to prove that the determinant of a Hermitian matrix is real. Um, Now, Hermitian matrices have this quality where H equals H dagger, that is, any Hermitian matrix is equal to its own Hermitian conjugate, right? So uh, the first line that we're going to do is just what we said before, that the determinant of any matrix is equal to the determinant of its own transpose, right? But we know on the right hand side that the transpose is just the complex conjugate of the Hermitian conjugate, right? H dagger um, complex conjugate. But then we can move the complex conjugate out of the determinant like that. And then we know that this is equal to just the determinant of H given the fact that it is Hermitian. So on the left-hand side, we have the determinant of H, and on the right-hand side, we have the complex conjugate of the determinant of H. They're equal, therefore, this is a real quantity. Is real. Awesome. Uh, the next thing that we want to do is that we want to prove that the determinant of a unitary matrix is equal to 1. So unitary matrices being ones where you have U dagger is equal to U inverse, or more concisely, that U dagger is equal to the identity matrix, right? Um, so we can take the determinant of both sides of this equation. Determinant U dagger is equal to the determinant of the identity matrix. We can separate determinants actually. So the determinant of two matrices multiplied together is equivalent to the determinants multiplied together. Yeah, that's what I'm trying to say. Uh, and the determinant of the identity matrix is 1. Um, and then on the left-hand side, we know that the Hermitian conjugate, again, is just the complex conjugate of the transpose, right? So, but then we also know that the determinant of a transpose is just equal to the determinant of its own matrix. So this is determinant U times the complex conjugate of the determinant of U equals 1. Now that is a mod squared of the determinant of U. So you have determinant of U mod squared equals 1. You can now take the square root of both sides, and you get the determinant of U is equal to 1. So, cool stuff there. Then the last thing that he wants us to check is for orthonormal matrices, that their determinant is either equal to positive 1 or negative 1. So the orthonormal matrices are kind of like the unitary ones, except that they are entirely real. So instead of the Hermitian conjugate equal to its own inverse, the transpose is equal to the inverse, right? And so this is going to be a pretty similar sort of deal. We know that O transpose will be equal to the identity matrix, so that the determinant of O transpose is equal to the determinant of the identity matrix. So the determinant of O times the determinant of O transpose is equal to 1. So we know that the determinant of O times the determinant of O, because, yeah, is equal to 1. So we know that the square, not the mod square, but the square of the determinant of O is equal to 1. Now if you take the square root, you get that the determinant of O is equal to plus or minus 1 from taking an actual square root rather than a mod square root. But yeah, it's plus or minus 1. Awesome.